Let's talk about one application closer to us. This, this too much, too many curves. So let's erase it first before we talk about the application. And that is the application that we talked about. We mentioned quite early because of the Cauchy-Riemann condition. If F is analytic, then both U and V satisfy the 2D Laplace equation, which is partial square U square partial square V, U partial Y square equals 0. And similarly for V, both U and V satisfy the same equation. Remember we talked about that? Still remember? Okay. You remember how to divide it? Use the Cauchy-Riemann condition, right? Yeah. Cauchy-Riemann because Cauchy-Riemann condition, partial U, partial X equals the partial V, partial U, partial Y minus, and you do another derivative, say partial square, partial U, partial X squared, becomes partial square, partial V, partial square, partial X, partial Y. And partial, take another Y derivative here, you see that the right-hand side is the same for both of them, except the negative sign, then you add the two. The reason they're the same is the order of the partial derivative is interchangeable. You can take partial x squared, partial x first, or partial y squared, doesn't matter. Partial y first, doesn't matter. Okay, so that's interchangeable. You add the two, you get this one, and similarly, you can divide the second one. Right, so that makes it very easy to find the solution of Laplace equation, which later on we'll talk about how to do this differential equation. But sometimes it's difficult to even find a function, right? But so this function of analytic function will help you. So as long as you write down the analytic function, you know that it's analytic, then you already found solution of Laplace equation. So that is helpful. Actually, very helpful. But sometimes when you solve partial differential equation, you don't just want to find solution. You want to find solution that satisfy boundary condition. The boundary condition can be very important in solving PDE. So, like originally on the complex plane, now we can extend it in two-dimension plane because now we're talking about real x and real y and function of real x and y on the xy plane. It doesn't have to be a complex plane, but you can look at it like a complex plane. But you can. This is just a solution of on the two-dimension plane. Say on the two-dimension plane, maybe you want to specify find the solution of Laplace equation over a certain curve that might be a little difficult to find to match this boundary condition. Say you want the solution as phi sub 0 u equals to phi sub 0. You want it to be a specified function that could be a function of x and y, or arbitrary, or just a number. It doesn't matter. See, you found you impose this boundary condition on the solution, then obviously not any analytic solution will satisfy this boundary condition. So whatever you specify a curve, you require the solution that satisfies the boundary condition. That make it much more difficult to find a solution, especially when the geometry of the boundary is complicated. But if you first found is a mapping to W, map to a W plane. If the geometry of this this boundary map to a simple boundary is like just a straight line. Sometimes if you can find a a mapping that would do that trick, that make the mapping, that make the satisfy the boundary condition much easier. The idea is now to solve the original problem, what you do is find a function on the UV plane. This is on W, the real part is U, the imaginary part is V, so this become a UV plane, right? If you can find a, say, a certain, if this is your map, this is your boundary, right? I should say this is your boundary, this is U, this is V, right? Right. This is C, right? Let's call this C sub W, this curve. Or maybe a straight line or simplified, much simplified geometry than the original curve. So, and if you can find a solution on the W plane, so basically W will satisfy the, if it W is analytic, right? And obviously W partial square W, or W is, I should say W, you find a solution of, let's keep it another name. Let's just say whatever Q, I mean, right, function of W, right? And it could have a real part, the imaginary part, so you have like all, it's a function of U and V, and that's fine. S, right? If you find an analytic function on the W plane, it depends on compact plane with W, it has the real and imaginary part like that. Obviously, by the same consideration, both R and S will be solution of the two-dimensional Laplace equation on the W plane. And then you want to satisfy that on this curve, U on CCW includes whatever the boundary condition you want to specify on the original curve, right? And this curve, that map from this original curve is satisfy the same boundary condition of this function. I should actually say not just Q or one of them, either depends on which one is easier. Right? Right. Because Q is a compact function. You want one of the either E or real or imaginary part that satisfy the boundary condition, right? Then the composite function will also satisfy the Laplace equation on that, because analytic function of an analytic function is still an analytic function. So that I think we had that homework before, right? When we show that the analytic function of analytic function is analytic. Say now the composite function Q becomes Q as a function of W as a function of Z. Right? That is the function that will be an analytic function. This means the real and imaginary part are also satisfying the 2D Laplace equation on the original plane. Then the real part, like the real part R as a function of U, which is the function x and y. It depends on U and V. V as a function of x and y. That will also satisfy the 2D boundary condition, because this is the real part of an analytic function on the Z plane, right? And then by the fact that this curve map to this curve and satisfy the same, that is the required boundary condition, this function will also satisfy the same boundary condition on this curve. Okay. Okay. So this is one way to find a solution of the Laplace equation that satisfies maybe a boundary condition on maybe more complicated curve, right? So that we actually will have homework probably to do something like that. Okay, so this is one motivation why we conformal mapping can be important, and there are many really complicated mapping that actually do this kind of trick. You can map some very strange curve on one plane to a much simpler curve on the other. That could be used to in this kind of solution. Yeah. Yeah, they separate in the real and imaginary part. Because U and V are the real part and imaginary part of W. So Q is a function of W and on this W plane. And we already said that W has the real part U and imaginary part V. Okay, so the real part and imaginary part of the Q with R and S will be function of the real imaginary part of W. Okay, yeah. So you can use one of them. So usually you don't need the other one. So this will be a complementary solution, but it might not satisfy the same boundary condition. In this application, the main objective is to find the function that satisfies the boundary condition. So you can use either one of them. So see which one has the correct functional form that allows you to match the boundary condition. Right. But this is a little bit abstract. And when you do your homework, you'll see that one part will be easier than to satisfy the boundary condition than the other part. So sometimes the real part is easier, sometimes the imaginary part is easier. Okay, so you have two parts. You found the part that make it easier to satisfy the boundary condition on the W plane. Then automatically the same boundary condition is satisfied when you write down the composite function. It's still a solution of 2D Laplace equation, but it satisfies the boundary condition on a more complicated curve. Either is fine, yeah. You don't need to be both. You just need to find one solution that satisfies the boundary condition, right? So and sometimes you find that only one of them is easier to satisfy the boundary condition. The other is more complicated. You cannot use that to satisfy the boundary condition. The solving partial differential equation in many cases is the main difficulty is to satisfy the boundary condition. So this is one way to help you to satisfy boundary condition. Find a solution that satisfies the boundary condition. Yeah, that depends on the question. This is this is just a motivation. Talk about a genuine method, genuine idea. But in order to see how specifically you actually do that, you need to find it. Consider a specific example. In our case, we have a homework problem that I suppose I already posed that. So I think it's the last question on this homework set. You have you have a chance to do this application. Okay. All right.